For more than a century, generating electricity has been a brute force physical process. We rely on immense heat, heavy friction, and the constant burning of fuel just to keep the lights on. We've engineered massive structures to dam entire rivers, using the crushing weight of falling water to physically spin giant mechanical turbines. Even our most advanced methods, like splitting atoms in a nuclear reactor, are ultimately just highly complex ways to boil water and create steam to turn heavy machinery. Contrast all of that heavy, loud machinery with a completely silent, elegant alternative, the modern solar panel. A solar panel has absolutely zero moving parts. It consumes no physical fuel and emits zero exhaust, yet it generates enough electricity to light up entire city streets. Generating immense amounts of power without a single moving machine might seem like magic. In reality, it operates entirely out of sight, relying on a strict, invisible relay race of microscopic particles governed by physics. The first step of that relay starts with the sun. What we experience as ambient daylight is actually a high-speed delivery system. Sunlight carries energy in the form of tiny individual particles called photons. After traveling millions of miles through space, the true energy transfer begins the exact fraction of a second these photons strike the surface of a solar panel. Beneath that glass surface, the panel is broken up into individual units called solar cells. These cells are built primarily out of silicon, a semiconductor material carefully chosen for its unique electrical properties. This brings us to the working principle of the entire system, the photoelectric effect. When an incoming photon crashes into a silicon atom, it transfers its payload of energy directly into the solid material and violently knocks a single electron completely out of its position. Multiply that single impact by billions of photons pouring in every second, and you suddenly have a chaotic swarm of freed electrons buzzing through the solid silicon. The photoelectric effect successfully captures the sun's energy, but there is an immediate problem. Energy without direction is entirely useless. Unbound electrons vibrating randomly inside a sheet of silicon do not constitute electricity. True electricity requires a disciplined, uniform flow. Engineers alter the internal anatomy of the solar cell, intentionally splitting the silicon into two highly specialized layers. Through precise chemical treatments, the top layer carries a negative charge, while the bottom layer is given a positive charge. Stacking a negative layer on a positive one generates an invisible electric field at the junction. When sunlight frees an electron, it's caught in this field. It can't wander randomly. The field acts as a one-way street, forcing electrons along a specific path. When millions of electrons are forced down that same path uniformly, you get a reliable, directed stream of power. This is known as direct current, or DC electricity. The dual-layer silicon structure essentially operates as an atomic funnel, catching unpredictable solar radiation and disciplining it into a highly organized flow of usable power. We now have a steady flow of electrical energy leaving the panel, but before it can actually light up your living room, it hits a technical wall: compatibility. Solar panels generate direct current. However, our modern power grid, and almost everything plugged into your walls, is built to run on a different format called alternating current, or AC. If you feed raw DC electricity directly into standard household electronics, they simply won't turn on. They require the alternating rhythm of AC power. To cross this final barrier, every solar system requires a crucial piece of hardware called an inverter. The inverter intercepts the incoming DC flow and actively translates it into grid-compatible AC power. The inverter successfully completes the journey. It bridges the gap between raw quantum physics and practical human utility, allowing the captured sunlight to finally push out through your wall outlets. By mastering this atomic exchange, we've built a way to generate immense, reliable power while entirely bypassing the need to extract or burn physical fuel. Because there are exactly zero moving mechanical parts in a solar cell, the system experiences no physical friction. It demands almost no maintenance, and the sunlight feeding it is infinitely renewable. This durability makes it uniquely versatile. It provides life-saving, reliable electricity in the most remote, hostile environments imaginable, even operating continuously in the vacuum of space. Yet that exact same solid-state technology scales down seamlessly in order to provide clean, localized energy to everyday residential neighborhoods. And when scaled up, massive industrial solar power plants operate across vast deserts, quietly doing the heavy lifting once reserved for coal furnaces and towering concrete dams. For most of human history, sunlight was just the ambient heat that warmed the Earth. Through the quiet elegance of semiconductor physics, we've successfully harnessed that light into a silent, powerful engine capable of driving our society into a sustainable future.